Let us now start lecture 5, colligative properties of solutions. Before going to define the colligative properties, let me first impose some conditions on the solutions. And the conditions or the criteria, conditions imposed on the solution. Condition 1, solution must be ideal. Solution must be ideal. I have already told that like this ideal gas, no gas is ideal, but a real gas, all these real gases behaves ideally whenever the P pressure tends to 0. Similarly, no solution is ideal. In fact, the non-ideal solutions behaves ideally under certain conditions whenever the solution is very dilute. That means when x1 mole fraction of this solvent in the solution tends to 1, means mole fraction of the solute tends to 0. Under this condition, the solution is very dilute and it behaves ideally. And I have also shown in the diagrams vapor pressure versus the mole fraction of the solvent. Now, whenever the solution is dilute, non-ideal solutions behaves ideally, these two curves merging together whenever this x1 tends to 1. So this solution may be called ideally diluted. Ideally diluted, and for this case, if this condition is being imposed for the solutions, then the Raoult's law is obeyed for this type of solutions. And second one, solute is non-volatile. Solute is non-volatile. Though no substance you can find which has no vapor pressures, but at ordinary temperatures we can say some substances are having the very low vapor pressures and they may be treated as the non-volatile solute. That means the solution is the volatile it means that non-volatile solute is dissolved in volatile solvent. This means that whenever we consider the two phases, one is liquid phase and the vapor phase. In case of solutions, the liquid phase is a mixture, but this vapor phase contains only the vapors of this solvent. And this third one, when a solution freezes at this freezing temperature, only pure solvent separates as a solid, and the solute will not enter into the solid solvent. Means the solute is not dissolved So in this case, the vapor contains only the pure solvent. In this case also, the solid contains only the solvent and no solute. Now I like to discuss the colligative properties. Which are termed as colligative properties, and how these colligative properties would be explained by taking the concept of the chemical potential. So there are four properties. One, a relative lowering of a vapor pressure. In short, we can write a relative RL Vp. And the second one, elevation of boiling point. Boiling point of the solvent. And the third one, depression of freezing point. Depression of freezing point of the solutions. And fourth one, the osmotic pressure. Osmotic pressure. So these are the four properties that will develop in case of this ideally diluted solutions. These are called the colligative properties. The Latin word colligative means to bind it together, and the main thing is that all these four colligative properties, in this case, they are binding together by the fact that all the magnitude of these properties only depends on the number of particles of the solute and does not depend on the nature of the solute particles. The particles may be ion, may be molecule, may be colloidal particles, but it only depends on, these properties only depend on the number of particles dissolved in a given amount of the solvent, not on the nature of these particles. Say glucose, fructose, or say urea, if the molecules are same, then all these three solutions will give the same amount, same magnitude of these colligative properties. So before discussing the main cause of these four properties, main cause for these properties actually the lowering of chemical potential. So before searching the main cause for the development of these four properties, we may give some relations. We may list some relations which may be useful to explain the origin of these colligative properties. These relations are the relations used to explain the origin of the properties, of the colligative properties. Of these dilute solutions. Number one relation, mu1 equal to mu1 naught plus RT ln x1. and mu1 is the chemical potential of this solvent when in a solutions where mole fraction of the solvent is x1, and mu1 naught is the chemical potential of this solvent whenever x1 equal to 1, means whenever the solvent is in a pure state. So this is number one relations, and it is clear that x1 is always less than 1 in the mole fraction of the solvent in solution is always less than 1. So ln x1 is less than 0, hence mu1 is greater than mu1 naught is greater than mu1. It is very striking that whenever the solvent we consider pure solvent, its chemical potential is greater, but whenever some solute is dissolved in the solvent, its chemical potential becomes lower, and this lowering of chemical potential is the origin or main cause for the development of these 4 colligative properties. And this lowering of chemical potential actually is an entropy effect. Say, I can explain in this way: mu1 equal to this H1 bar minus T S1 bar. Mu1 is the partial free energy of this solvent, which is given by the name chemical potential of the solvent by Jane Lewis and me, and this one is the partial molar enthalpy of the solvent. This is the temperature, and this one is the partial molar entropy of the solvent in solution. So whenever the solute is added to the solvent, the randomness of this solvent is increased, and we know that entropy is a measure of this randomness. Randomness is increased means entropy is increased, so this term will increase. But since the solution is taken ideal, so this partial molar enthalpy of the solvent is not changed. It remains the same, and this one is fixed. So as this one is increased, so chemical potential of the solvent is decreased. So decrease of chemical potential of the solvent in solution is an entropy effect. The second relation, del mu 1 by del T at a constant pressure is equal to minus S1 bar, and S1 bar is positive always. So since this one is positive, so this derivative is negative. It means that whenever the temperature is increased, the chemical potential of the solvent is decreased, or any substance. For any substance, whenever temperature is increased, the chemical potential of that substance is decreased. Or in a reverse way, I can say whenever the temperature is being lower, then chemical potential becomes higher. And also, you know, the entropy of the solvent whenever it remains in vapor state, is greater than this chemical potential when it is in liquid, and greater than whenever it is in solid state. Since randomness in the vapor is much more greater than the liquid, than the solid, and naturally with the same rise in temperature, there will be more lowering of chemical potential for whenever the substance remains in, when the solvent remains in vapor phase, and less in liquid state, and again least whenever the solvent remains in solid state. And this third relation del mu 1 by del P at a constant temperature is equal to V1 bar, partial molar volume of the solvent, and this V1 is always positive, so this is positive always. It means that if we increase this pressure, then chemical potential of the solvent will increase. With increase of pressure, chemical potential of the solvent will increase. So these are the three relations I shall correlate to explain the origin or the development of the colligative properties of this solution. Now I shall try to explain the four colligative properties one after another by using the concept of this chemical potential or using these three relations that I have listed here. And you know, first colligative property, say relative lowering of vapor pressure, and it is P1 naught minus P1 divided by P1 naught. This is to be explained first. For that, let us consider the two closed container, and here the pure solvent at this temperature T is constant, and constant T can be kept by keeping it in thermostat, and here the vapor, solvent vapor, and this is also pure state. So chemical potential of this pure solvent we can write mu1 naught, and this chemical potential measures the escaping tendency of the solvent to escape from this pure solvent, from the liquid phase to this vapor phase. This is the existing phase and this is the phase available. So this is the definitions or physical interpretation or physical significance of this chemical potential. Chemical potential also measures the escaping tendency of the substance when it exists to the state which is nearby available. So this will move to this one, and another container, similar container at the same temperature. Here it is closed system. Here the solution. Here it is non-volatile solute in volatile solvent. And it is in liquid phase. And here it is a pure vapor, pure solvent vapor phase. Pure solvent vapor phase. As you know, the solute is non-volatile, so it will not be vaporized to occupy this vapor. So here the chemical potential is mu1. Chemical potential is mu1. Mu1 is the chemical potential of the solvent in solution. It is the chemical potential of the solvent, pure solvent. So this also measures the escaping tendency of the solvent from the liquid phase to the vapor phase. And here also the same temperature. Same. From these relations, it is clear that mu1 naught is greater than mu1. means escaping tendency of this pure solvent to the vapor phase is greater than the escaping tendency of the solvent in solutions to this vapor phase. Naturally, as escaping tendency greater here in this case, so vapor pressure will also be high. So in this case, this P1 naught is greater than P1. So this vapor pressure over the pure solvent is greater than vapor pressure over the solutions. So naturally P1 naught minus P1 is called lowering of vapor pressure of these solutions, and P1 naught minus P1 divided by P1 naught is called the relative lowering of vapor pressure of the solution, and this is a colligative property, and this property depends on the number of particles, solid particles, not the nature of the solid particles. The second one, now the second colligative property is the elimination of a boiling point. Elimination of boiling point of this solution, and it is denoted by del T A. Del T B. B means boiling, and del difference in temperature for this boiling point in case of the solutions. So in this case also again I can here take this container and this closed container, and here this piston. It is a piston, and this piston is at this pressure P, and naturally P usually taken as 1 atmosphere. And here the pure solvent, and here also pure liquid solvent, and here it is pure vapor solvent. And it is the temperature. Or you can say the normal boiling point of the solvent at which the vapor pressure becomes equal to 1 atmosphere. So this temperature is denoted by TB naught, not for the pure solvent, and TB, the normal boiling, it is called normal boiling point. Normal boiling point is defined as the temperature at which the vapor pressure over the solvent is equal to the 1 atmosphere pressure. And in this case, mu1 liquid is equal to mu1 not liquid equal to mu1 vapor. Both are equal. At this pressure 1 atmosphere, at this temperature TB naught. Second, if we draw the same diagram, but instead of this pure solvent, here the solution of a non-volatile solute. Non-volatile solute in volatile solvent. When the solute is added, its chemical potential is decreased, and this is suppose mu1L. This is mu1L, and here the vapor. Here the pure vapor of the solvent. Here also pressure is 1 atmosphere. So the solution, at this temperature and at this pressure, this one not be equal. This will not be equal. At here it is equal, but here it is not equal, and mu1L becomes less than mu1V. Actually, at this at a temperature TB naught and pressure 1 atmosphere. So the solution will not boil. In order to boil these solutions, again these two terms should be fixed, should be constant, should be same or equal. Then again the equilibrium will be established. So this could be equal only when this one decreased and this one is more decreased than this one. So in this case, we have seen if the temperature is increased, then mu1 is decreased. Naturally, if we increase this temperature greater than TB naught, then both this one and this one both will decrease. But the chemical potential of this vapor phase is decreased more than the chemical potential of the solvent in liquid phase. So this one also decreased, and this one also decreased, but this lowering is much more greater than this one. Again, at a temperature TB, boiling point of this solution, this mu1L becomes equal to mu1 naught V. That means at this temperature, both again these two becomes equal. So naturally this one is a higher temperature than this one. So TB is greater than TB naught, or TB minus TB naught is equal to delta TB and elevation of the boiling point of these solutions. So elevation of boiling point of the solutions could be explained on the basis of the chemical potential. Whenever the pure solvent we have considered, these two are the same. These two same at this pressure 1 atmosphere, temperature TB naught, and this is normal boiling point. And whenever this solute is added to this solvent, it becomes a solution, and chemical potential of this solution, chemical potential of the solvent in solutions is lowered down, and these two are not same at this temperature TB naught. Temperature to be increased, temperature to be increased, then at high temperature TB, again these two becomes equal. As the temperature is increased, chemical potential is decreased, and chemical potential of the vapor becomes much more decreased than the chemical potential of this liquid. So the third one, now consider the third colligative property, depression of freezing point of the solutions, which is denoted by del Ta. Let us consider the pure solvent when freezes, pure liquid solvent when freezes, it becomes these two terms, chemical potential of the solvent mu1 naught L is equal to mu1 naught S. These two are same. So whenever the chemical potential of the solvent in two phases are equal, it is in equilibrium, and this temperature is called the freezing temperature of this pure solvent. But whenever the pressure is taken 1 atmosphere, this one is called normal freezing point of the solvent. And at this normal freezing point of the solvent, at this temperature Tf naught and 1 atmosphere pressure, these two becomes equal. Means mu1 naught L equal to mu1 naught S. But whenever the solute is added to this solution, it becomes a mixture and chemical potential is being lowered. Mu1 L is lower than mu1 not L, and at this temperature and pressure, these two are no longer equal. These two are no longer equal at this Tf naught and T atmosphere. Again, these two becomes equal at this lower temperature. Whenever the temperature is lower, chemical potential is increased. From this relations we can see it. So both the mu1L and mu1 not S both will be increased, but in case of the liquid, the increase is more than this one. Again, this is the lower, this is greater, but with the lower temperature, this will increase more than this one, and this two becomes equal at this temperature, lower temperature, and this temperature is called the TA, means freezing point of these solutions. So freezing point of these solutions is lower than freezing point of this pure solvent. So this difference of these two is called the delta Tf, and it is the depression of freezing point of these solutions. Fourth colligative property of these dilute solutions, osmotic pressure. Osmotic pressure. Let us take this U container like this U tube in both the limbs. Here it is solvent, pure solvent. Here it is the solution. And solvent and solution both are separated by a semi-permeable membrane. Semi-permeable membrane (SPM). Semi-permeable membrane is the membrane which allows the solvent to pass through, but it restricts the flow of this or movement of this solute particles through this semi-permeable membrane. So when at the same pressure, both this is piston, this is one piston, both the pistons are at the same pressure, P and P, temperature is T. So at the same temperature pressure, and this is the pure solvent, this is the solutions, and here the chemical potential is mu1 not L, here the chemical potential is mu1 L. So we know that the chemical potential of this pure solvent is greater than chemical potential of the solvent in solutions. So the chemical potential have another physical significance is that it measures the any matter or any substance will move from higher chemical potential to the lower chemical potential until it becomes equal. So these two are not equal, so this solvent will move from the solvent side to the solution side spontaneously, and this spontaneous flow of solvent from the solvent side to the solution side is called the osmosis. If we like to check or stop this flow of the solvent, then we shall have to add some additional pressure. This is pi, additional pressure on the solution side in order to stop the osmosis. So whenever this pressure is additional pressure is added, again this mu1 not L becomes mu1 not L at a temperature mu1 not at a temperature T and pressure P is equal to mu1 at a temperature T and pressure P plus pi. As you know, with the increase of this pressure, the chemical potential is increased. So this one is less, but with increase in pressure on the solution side, its chemical potential is increased, and the pressure in that case becomes P plus pi, temperature remaining same, and these two are equal, and the flow of the solvent will stop, and these two sides are again attain equilibrium. So this is the explanation why the osmotic pressure is developed when the solvent and solutions are separated by a semi-permeable membrane, and it is also gives the definitions of this osmotic pressure. Osmotic pressure is the pressure, excess pressure added to the solvent side in order to stop the osmosis. This is all about the 4 colligative properties. The elevation of boiling point and depression of freezing point could be more clearly shown in the form of a diagram. And chemical potential versus temperature plot is here, and we have 4 curves. This curve is a pure solid solvent, this curve pure liquid solvent, this one is pure solvent vapor, and this one is the liquid solvent in solution. So these are the 4 curves, and these curves are drawn according to this formula. This chemical potential of the solvent, liquid solvent in solution is less than pure solvent, and also here you can see the change or decrease of the chemical potential with temperature is the highest in case of vapor, lowest in case of this pure solid, and in between this liquid. So this curve is drawn according to these 3 relations, and here in this case the chemical potential of this pure solvent, vapor is equal to the chemical potential of this liquid. So this one becomes the freezing temperature, boiling temperature of this solution. And in this case, here it is the mu1 naught V equal to mu1 naught L. So this will be this condition, this equality occurs only when the temperature is a TB naught, means a boiling point of this pure solvent. Similarly here actually this mu1 naught liquid equal to mu1 naught solid. So this will be the freezing point of this pure solvent, and in this case the mu1 L is equal to mu1 naught S. So this will be the freezing point of these solutions. So freezing point of these solutions is lower than the freezing point of this pure solvent. Here the boiling point of the solution is greater than the boiling point of this pure solvent. So this one is difference is delta TB, this difference is delta TF, and this difference is delta TB. And if you consider the magnitude, then delta TF is much more greater than delta TB. This will be fully illustrated in a sort of problems in the coming classes. So this diagram can more clearly illustrate why the boiling point is elevated and the freezing point. Boiling point is elevated and freezing point is depressed in case of the solid is added to the solutions. This is all about these colligative properties of these dilute solutions. Thank you all for watching this video.